All right. Hello, everyone. Thank you for indulging me that. I'm actually a big John Prine fan, so today is a rather sad day. Um, but thank you for indulging that. I know that probably isn't anyone here's taste in music. But with that, and I killed the stream briefly just in case anything here gets muted because of the music. So I skirting around it, but whatever. Um, Anyway, today we're going to pick up with Concurrency Part 2. So, just some announcements. Homework 5 was posted this morning. It is due next Friday, so that will be April 17. Um, from there will be a Homework 6. We're going to start covering material for that next week. Um, from there, sorry, my headset makes random noises sometime. From there, um, we, of course, are still working on the exam scores. We hope to get those back to you soon. We're meeting with the TAs today to figure out how we're going to actually grade them. But we hope to be able to have it by the end of the week. I don't want to promise that. And certainly we're working already on the homework 4 grading. So not too many announcements today. Next Friday and Monday, we're going to be talking about recursion. There will be a quiz this weekend, so be aware of that. Um, Recursion and concurrency are part of homework 5. So there's two parts to it, but they're a single submission, recursion and concurrency. It's not a lot of code. The only tricky part has to deal with thread concurrency and handling race conditions, which we'll talk about today. With that, are there any questions to get started? Otherwise, I will just go ahead and pick up where we left off on Monday. Hmm. Give me 1 second to check something here. There we go. Okay. All right. So to pick up where we left off on Monday, we were talking about this program that manages a bank account and how we were going to create a number of threads that each performed $100 deposits 100 times. And what we ran into was if we just create the threads in this way, and the threads simply call deposit, and we take a look at the bank account deposit, a problem that we ran into, and I'll just bring up the whiteboard again so I can diagram what the problem was. A problem that we ran into was that you would have two threads, thread 1 and thread 2, both accessing this balance at the same time. And it's actually worse than that because we could have this with more than one thread. So balance, let's say balance for 1000 and these two threads were both calling deposit. So they both call deposit. Well, what could happen is if we take a look at how the code for deposit is written, you can see that both threads could inevitably run this line of code before they run this line. So double new balance equals balance plus amount, and balance equals new balance. Let's take a look at what that could do. If thread 1 were to run this statement first, and remember thread 1's depositing $100, thread 1 creates a variable called new balance equal to 1000 plus 100. Thread 2, it then pauses. Thread 2 picks up. Notice balance is still 1000. So it says new balance equals, again, 100 plus 1000, 1100. Then thread 2 says balance equals new balance, that fourth line of code. So it's going to update balance to be 1100. And this thread is done. And then thread 1 finishes, and it also updates balance to be new balance. But if you see new balance is 100 or 1100, it updates that. So we've deposited twice. but we have only changed the balance by one deposit's amount. And that's the problem that we're running into. And we have the same problem with withdrawal. We also have the same problem with balance and withdrawal kind of working in concert with each other. And the result of this is when we run this code, you'll see that even though I'm doing the same number of deposits and balances, I don't get the same output. I get 2200 here rather than 0, which if I'm depositing X and withdrawing X, I should end up with 0. I should end up with net 0. So why don't I? And in fact, if I run it again, I mean, this time you'll see I get negative 6400. That's really bad. That's way off. Negative 8000, even more off. We're getting worse. What, 1100? Okay, not too bad. The problem that we have is that these two threads are exhibiting what we call race conditions. That is, because of where the threads pause, they're accessing a variable, but they're getting an out-of-date value. So going back to the whiteboard, thread 1 got the value of balance first. It got 1000 first. Thread 2 later got 1000 before thread 1 updated the balance to reflect the new deposit. Now you may be thinking, okay, well this is just as simple as, don't have multiple lines of code. Instead, just have one line of code in this deposit function. We don't need all this printing. We can just say balance plus equals amount. You might think that will solve the problem. And then for withdraw, balance minus equals amount. Well, if it's only one line of code, it can't be interrupted, right? Well, we'll see. If you remember the face I made when I would say something is right, but it actually wasn't, it was like this. I'm going to make that face here because that won't solve the problem. When I run this code now, first off, we're actually not doing any printing. So what I'm going to need to do is just do system.out.println. And then let's just do account.getBalance at the end. Let's see if this amount is 0. 900. It's not. 300. 200. Negative 100. I'm not getting the same value, even though I'm doing the same number of deposits and withdrawals. And the reason is this. To a human being who's reading Java code, this may look like one line of code. But at a machine level, it is not a line of code. At a machine level, this is actually 5 instructions. And what happens is, within those 5 instructions, and actually it can be more than 5, but at a simplest level it would be 5. The thing is, we can be interrupted in between those 5 instructions at any point. Even though this is one line of code at the human Java level, at the processor level, it's several different operations. And so what we need to do is first recognize this is a section of code that we do not want interrupted, which by that I mean we do not want to switch to another thread that accesses balance at the same time. That's the rule we're going to set up. And a general metaphor that we use for this is called the dining philosopher's problem. And the dining philosopher's problem, which is admittedly a little bit gross and it's certainly not, certainly could help spread coronavirus if you were to actually do this right now. The idea is we have a table, and we have 5 philosophers sitting around the table. And there are 5 chopsticks on the table between each philosopher, such that there's a chopstick to each philosopher's left and a chopstick to each philosopher's right. Each philosopher also, and I know I'm such an amazing artist, this is basically a Bob Ross stream at this point. Also, we have each philosopher with a bowl of rice in front of them. And the philosophers do two things. Thank you for the Kappa Ross, by the way. The philosophers do two things. They think and they eat. Now, the philosopher doesn't need any resources to think. They can just think all on their own. But they do need resources to eat. Specifically, this philosopher, and I'll switch to green here for a second, needs both chopsticks to be able to eat. So this philosopher needs both chopsticks to be able to eat. And the idea is each philosopher can only use the chopstick one at a time. That is to say, if let's call these philosophers A and B. A and B cannot eat at the same time because they both rely on a shared chopstick and only one person can possess it at a time. And so what we need to do is we need to set up a means to say, hey, this resource is protected. Only one person can use this resource at a given time. And so the way we do this is through something called, and you may have heard this term before, something called semaphores, which in Java, and actually I just realized the green does not show up well here. In the Java, we were just going to generally call them locks. A and D, yeah, that's, the exams will be, so I called them A and B, but admittedly the green doesn't show up well. I did answer that, which is to say we don't have a firm deadline yet, but hopefully by the end of the week, we're meeting with our TAs today to discuss what's feasible. There we go. I will avoid using green because the green just does not show up on the camera. I tried to play with the camera color settings to get the green to show up better, but I think the green markers just suck. So, semaphore. Oh, right. So A and D in this case, so like if D is down here, A and D don't affect each other. They don't share a resource. They can both eat at the same time. Yes, if that's what you were asking. I like the creative solution, Ramsey. Okay. So, what we're going to do, and if you'll notice, first I have a lot of different projects open, and if you go to the, by the way, homework 5, as I said, posted due April 17th at 11:30. That is next Friday. And homework 5 is not a lot of code. It's probably less code even than homework 3. So it's not designed to be super tricky. Anyway, if you go to, and I just want to show you this, the resources, if you go to my code examples, you will see that I have 5 different folders. I haven't filled in thread example 5 and thread example 6. I just want to point out that thread example 4, that is the thing with the race conditions. This one will not work. Homework 5 and 6, or thread example 5 and 6 are going to be solutions to this problem. And let's start, since it seems a good idea to increment, let's start with 5. So I'm going to close out. And the first thing I want to note is 5 is the same problem. We have a bank account. We have something that generates 100 threads that deposit $100 100 times and withdraw $100 100 times. And then we have our deposit runnable. This function has not changed. It works exactly the same. And we have our withdrawal runnable. This function has not changed. Works exactly the same. So we haven't changed how these functions work. What we have changed is bank account. And in bank account, we've created this thing called a lock. And if you look up at the top, you will see an import statement. We have 2 different import statements here. We have a lock and a reentrant lock. A lock is the abstract class. A reentrant lock is the concrete thing that implements the lock. And what you'll notice is I declare at the class level a variable called balance change lock. And in the constructor, I initiate that lock by saying new reentrant lock. This would be the same as saying list L equals new array list. The reentrant lock is just a concrete way to implement the lock interface. And now let's take a look at how I use that lock. So if you'll notice, inside of the deposit function, whenever I enter this function, will Eclipse prompt us to import those? It will typically just make sure you're importing the correct lock, just to show those import statements again, and I'll paste them into chat for you. Make sure you're importing the correct one. Do you need a lock for each field? So we'll talk about that. We will talk about that. From there, all you do whenever you need to access a shared resource, that is to say you want to make sure that no race conditions can occur, before you make any changes, you're going to lock the balance. Then you're going to perform your code, and then before you leave, you unlock. And I want to just highlight a couple things as to why we have a try finally. Remember that with the try catch finally block, finally executes even if the try catch crashes, even if it's with an unhandled exception. So finally executes no matter what happens. Crash, no crash, doesn't matter. And the reason is, the thing about this lock is this, going back to our dining philosophers. If A picks up this chopstick and never lets it go, if A picks up this chopstick and it never lets it go, B will starve to death. And that's because B can never eat, because A is being greedy and never lets go of that chopstick. B will never be able to run. So is the other thread sleeping while the thread is locked? Yes. Doesn't this defeat the purpose of threads if they can't run at the same time? So that's a great question, Jules. So the problem that we run into is there is no solution. There is no solution to race conditions that can be solved without some form of bottlenecking. That is to say that now all the threads need to wait for their turn to execute a certain thing. That is true. What we can do with threads, and you'll see an example with merge sort, and I'm just going to now pull this up. I actually, with merge sort, I do a means of, where is the... There's a synchronized block in here, I thought. Hang on. Actually, no, that's right. I managed to do it without a bottleneck. Sorry, I forgot about that part. But oftentimes you will find in your threads that you don't have a choice, that you have to do some kind of bottleneck to prevent changes. The key is we can do anything that is outside of modifying these values, outside of the block. So anything that doesn't change balance, we can do before we lock balance. So for example, this print statement actually doesn't need to be in this lock. I can put it before. And believe it or not, printing actually takes a lot of time. So this is going to make my bottleneck shorter. It's going to take less time. And so yes, it does. You do lose efficiency when you use locks. You're exactly correct. But what you can do, again going back to the whiteboard, the question that was asked earlier, can A and D at the same time? They can. A can have both of these chopstick semaphores, and D can have both of theirs. And sure, B, C, and E can't run right now. They need to wait for a chopstick. But A and D can run at the same time. Because even though they're both using a protected resource, a resource that we lock in this case, um, their resources don't overlap with each other. And so we'll show an example of that in a minute. So, yes, we do lose runtime efficiency. You are correct about that. But there's a trade-off there where we gain some benefit as well. Wrong screen. There we go. So now we do the same thing with deposit as we do with withdraw. We have this lock. And the idea is when you hit this line of code, the program, when you hit this line of code, the program, or the thread, excuse me, the thread will try to grab the lock. If the lock is unavailable, that is to say another thread already has it, this thread waits. That is to say it will effectively put itself to sleep for a period of time, and then it will check back later. Think of it like if you go to the bathroom in a restaurant, you could wait outside the door, or you could say, it's occupied, go and sit back down, and then just check back later and see if it's open then. What was the instance variable balance declared as again? It was declared as a re-entrant lock, a new re-entrant lock. So we define our lock at the class level, we initialize it in the constructor, and then from there, we simply use lock and unlock. And going back to the whiteboard, lock is when A picks up the chopstick, and unlock is when A sets the chopstick down. So if A were to, say, unlock its left chopstick, we erase the lock isn't there. I know, once again, fantastic art skills. Where did there it is. The chopstick is now available for B to pick up because A is no longer claiming it. And again, the reason we want this finally unlocked, the reason we want this here is we want to always make sure that no matter what happens, we release the lock. That is to say that there's no situation where the thread dies holding the lock. It should always release it before it goes. So now let's run this code. Oops, sorry, ran the wrong program there. So this is... Now you'll see the balance is 0. We do a bunch of deposits, we do a bunch of balance changes, etc. But now, no matter how many times I run this program, the balance that we end with is always 0. And it's because we never have the problem of race conditions. Can you set the variable to wait a certain amount of time before it tries to see if the bathroom is available again? Not directly, no. And in fact, you could, if you wanted to, set something like that up, but you don't really need to. If you're doing a thread type architecture, you just trust the threads to handle themselves. So there's only one thread of the two need to be locked. Well, there's not two threads. There are in this case 200 threads. But the key is, let's say now let's take the dining philosophers to an extreme level. Let's say that now instead of 5 chopsticks, one between each person, that there's only 2 chopsticks in the center of the table. There's only 2 chopsticks in the center of the table. Now at this point, only one philosopher can eat at a time. So you can think of this like the philosopher A goes and locks the chopsticks. C then tries to get them, but has to just wait here. And eventually it will check and see if the chopsticks are available. And the point is, C won't be able to run until both A has set the chopsticks down and then C has woken up to see if the chopsticks are still available. The point is, in this case, there's actually, if you think of the pair of chopsticks as a single entity, there's only one shared resource. And that's more apropos of what's happening here, where only one of the 200 threads can be messing with the balance at a time. There are 3 chopsticks. Oh, yes, good point. Sorry, I thought you were making like a Star Trek Next Generation. There are 4 lights crack there. Can you put checking to see if the chopsticks are available on a loop? You can, but you don't want to. The thing is, the thread... So this is where generally the rule of programming is as followed. You don't want to try to do everything yourself. You don't want to reinvent the wheel, because trust me, your wheel's not going to be as good as the wheel that someone else made. And so, you're going to rely on the thread class which already handles this. Is it possible to control the order of the next threads? No. And that's actually very important. It is not possible to control the order. And that's because threads are inherently chaotic. You cannot predict, just as we talked about last time, you cannot predict the order the threads will run in. And if you can't predict it, then you can't control it. So, could you put them in a loop? Sure, but we're not going to in this case. We are going to use a loop in a second to check a condition, but that's going to be something that we add on called a condition. So we'll get to that in just a second. So let's take a look at this balance here. And you'll see actually this, there we go. Notice at some point, so if many different threads share one variable, you can only include a lock in one of them. So again, all of these threads are accessing the same lock. There's not a lock in one thread. All of these threads are accessing the same lock. But think of it like a bathroom again. Only one person can be in there at a time. But you don't have a nice orderly queue of people waiting for the bathroom. It's just a free-for-all to get into the bathroom. Think Hunger Games meets going to the bathroom, I guess. That would be more apropos. And so there's only one lock for the class. Bank account. Now, if I had multiple bank accounts, each bank account has their own lock, because I define this at the bank account level. You can have multiple locks if you have multiple variables. But in this case, I only have one. Let's say, I don't know. This is going to be incredibly contrived. Understand that this does not make sense what I'm about to do, but it's to answer a question. Let's say I had some other variable in this bank account called X. I don't know why I would have this, but let's just say I do. And I have a function called public void incx, and that does x plus plus. And I have public void decx, and that does x minus minus. And then finally, I have a method public void getX, and this is just going to return x. I don't know why I would have this in a bank account. I want to be really clear, but I'm answering this question. How does the lock function know which variables to lock? It doesn't lock variables. I want to be really clear. It locks lines of code. Balance is not the bathroom in this metaphor. This is not the bathroom. The bathroom is this. This code is the bathroom. Only one program can be in this code. And the reason it's this code is because it's in between lock and unlock. Would balance be like the location? No, balance is a number. Balance is a number. It's just a number. That's all it is. But we, as programmers, recognize that we need to protect this number, and so we only modify that number in the bathroom. Which, again, this is getting really awkward, but whatever. The point being, this is the bathroom. This is the only place we modify balance. Why isn't there a catch statement? Because we're not expecting any exceptions. We're just making sure that if for whatever reason this code crashes. It could crash because of an out-of-memory exception. It could crash because any number of reasons. Whatever. No matter what happens, we know for certain that we will release the lock. Is there a lock in the withdrawal runnable? No, because I'm not in the deposit runnable. Again, this is in the class bank account, and the block is tied to the bank account. Deposit runnable and withdrawal runnable have no locks. There are no locks here. You will not find any. Because I'm not locking deposit or withdraw, I'm locking code within those functions with the same lock. And the reason I'm locking it is because this code modifies a variable. It doesn't. I want to be really clear. How does the balance lock get tied to the balance? It doesn't. I, as a programmer, tie it. And the way I tie it, again, from the time I open this lock to the time I close this lock, no one else is allowed in here. And it turns out that the only place I modify balance is inside of these locks. Do I have to do it that way? No, the code will compile if I don't do it that way. But if I don't do it that way, I'm not making my code thread safe. So if I delete this lock like that, this code compiles and it runs. It just won't be thread safe anymore. So there's balance change lock is not magic. It's not quantum entangled to balance. They're two different things. But I make sure as me, the programmer with a brain using my human brains and stuff, I decide, not the computer, I decide to only modify balance inside of that lock. It's a human decision. It's not something that's happening within Java. The reason this code is protected isn't because of some magic thing having to deal with how Java works. It's simply because it's in between when I lock and when I unlock. That's the only reason it's protected. So can you modify multiple variables with the same lock? Sure. You can modify a billion variables with one lock. But now I'm going to explain why you might as well have multiple locks. So I want to illustrate this quickly. So I'm going to do sorry, this should be int. So I added this x for no particular reason. And now I'm going to go into my deposit runnable. And in my deposit runnable, after the delay, I'm going to call incx. Just inc account dot incx. And then I'm also going to call in withdraw account.decx. And again, I'm only showing this to say, what if the class has multiple variables? Now, right now, I have not put any lock protection at all on X. I have not. For whatever reason, I haven't done so. This is just to prove a point. Then from there, I'm going to do system.out.println account.getX. And if I did this correctly, when I run this code, that's strange. Not printing, sorry, 1 second. Oh, x is never set equal to anything. Yeah, that's a good point. X equals 0. Here, let's do it here. X equals 0. Let me make sure I'm running the correct. Can you explain why we have to make things thread safe? Because if we don't make things thread safe, go back and look at the beginning of the lecture where my deposit and withdraw didn't work. And the reason it didn't work was because the code wasn't thread safe. So that's the only reason I can give. I'm not going to replay it. What do you mean by instantiate X? I do up here. No, it would default to 0 because it's an int. There is no null int. I have an issue where this function is not printing. Hang on. Let me see if I'm even reaching this line of code. Yeah, I'm not reaching this line of code for some reason. Something weird is happening here. No, you're incorrect on that. Ints can never be null. Try printing before the for loop. Well, if I print before the for loop, I've never actually run those threads. No, the threads have stopped because the program terminated. I'm having a weird issue here. I'm trying to prove this point, but I'm doing a really bad job of it. This worked when I practiced it, I swear. Yeah, I think what might be happening is I might not be running the correct. Let me make sure this is thread example 5, thread example 5. Oh, I know what's happening. Duh, I know what's happening. Give me a sec. It is printing X. X equals, I know what's happening now. Plus, so I'm not going to answer questions from 15 minutes ago at this point, and I apologize for that, but it's getting very difficult for me to proceed with the lecture. So I'm going to have to cut off questions from previous contents. Until and I'll happily answer them after lecture. I want to be clear. I have to get past this, and I apologize that I've wasted this time. That's what I did wrong. So it is it's actually printing if I do x equals. It's somewhere in here. I can make this work with threads.sleep. What's happening is it's printing before the program actually ends. And so I'm just going to put this thread to sleep for a second. That way it prints as the last thing. There we go. X equals -12. All right. So because X is not 0, that means X is not thread safe. We can fix that, and we could very well use the same lock. Balance change lock dot lock, and then balance change lock dot unlock. We could do that, but the thing is that this lock really exists to protect the balance variable. Again, it doesn't do that magically. We do that ourselves. But there's no reason that this needs to be one lock protecting both variables. What I could do is I could just create a second lock, X lock, and then I initialize that. X lock equals new re-entrant lock. And there are other locks. We're not going to use them in class. And then from there, I simply do xlock.lock, xlock.unlock. So you make a lock on all the variables you want to protect. Effectively, yes. If two that's effectively the broad solution that I would generally use. Yes. And it might be that you have a reason that you want one lock protecting two variables. And you can do that, but you don't have. But you can always do separate locks. And so now, oops. Oh, right. I'm not gonna lock. I don't need to lock the return because there I'm just printing. I'm not modifying the value. And so now, if you notice, no matter how many times I run this, X will be thread safe. It will be 0. Is the reason you shouldn't use one general lock. Again, going back to the dining philosophers, the reason is if I only have one pair of chopsticks, and let's say that this chopstick is account or balance, and the right chopstick is X, then only one philosopher can eat at a time. But if I have, say, 5 different locks, again, one between each philosopher. Stuart, can you stop meowing? Thank you. If I have one between each philosopher, D and A could eat at the same time, and it wouldn't be a problem. So that is to say, we could still have concurrency. Whereas if we only have one lock, then we don't get that. If all the variables in your thread are locked, it's theoretically any faster than not using threads. Again, if the key here, and I'm gonna have to just say go back and rewatch the thing if I get this question again, because I've unfortunately answered it, I feel, multiple times. In this situation, you don't have to lock all of your code. You only need to lock the part of your code that actually has a risk of creating race conditions. That is when a variable is modified. And so, if the situation is that we could have race conditions, then we have to lock it whether we like it or not. But we don't have to lock the entire code. Notice I'm not locking the entire code. This print statement here has nothing to do with modifying balance, so there's no reason to put it inside of the lock. Since runnable classes are ones that have to do with threads, why don't we put locks in runnable classes? Because we're not locking a thread. Understand, this variable belongs to the bank account. Each thread does not have its own bank account. There's 100 threads that all have the same bank account. There's 100 different objects that are all using the same. So imagine, like, if this marker were my bank account, imagine 100 hands coming out and holding onto it. All of them are using the same one. The bank account's the thing that needs protected. The threads don't need protected. All right. I need to move on. The last thing I'm going to show is a problem that we run into with this bank account. I'll scroll up until I find it. And maybe I got a bad example here, but I'm not going to answer any more questions for the time being. I apologize. There we go. I saw it at the top. Notice right now we have a negative bank account. Now, I don't know if any of you have ever worked with a bank, but they tend to not like you having a negative bank account. In fact, they will actively stop you. If you have a negative bank account, they will charge you money, thus making your bank account even more negative. Yes, it makes all the sense in the world. But the point is, the bank, we don't want it to let you ever dip into the negative. So what we need to do, in addition to managing our locks, is we need to make sure that we never go below a negative balance. So how can we do this with threads? Well, the way we're going to do it, and this is thread example 6 that I'm going to show. The way we're going to do it is this. Deposit hasn't really changed. There's this thing, but don't worry about this thing yet. Otherwise, deposit hasn't changed. Again, I'm going to move that print statement up before the thread here. And same with the withdraw. But now you'll notice that in withdraw, we have this while loop. We have this while loop. And what this is going to do is this is going to make sure that we never proceed while there is a negative balance. But we have a problem. Because so far we've only had one lock. And what happens if we enter a while loop with the lock in our hand, but the balance being the balance in the amount being such that we can't do a withdrawal? Well, the problem is we would be stuck here. An example of this, going back once again, is let's say we have this problem with dining philosophers. Let's say that every philosopher is holding the chopstick to their right, but no philosopher is holding the chopstick to their left. If you look at this, the problem is fairly obvious. All the philosophers are holding one chopstick, but no philosopher can actually eat. And this is called a deadlock. And when a deadlock occurs, one of the philosophers needs to give up their chopstick so another can eat, so he can release his chopstick, so another can eat, so etc., and so on. So what we have here is we have, sorry, that was a bit awkward. We have an extra variable, and this is called a condition. And the condition is something that we add to an existing lock. And what this enables us to do is this allows us to say, hey, we're not going to proceed with this lock until some condition is met. And the way we do that is below in the withdrawal function. So we still have the same lock, that hasn't changed, but we have this sufficient funds condition. And what this is going to enable us to do is it's going to enable us to temporarily give up a resource, but then get it back later and proceed from where we left off. So, deposit, for now, the only thing we've added is this. We'll talk about that in a second. I'm going to skip it. Otherwise, deposit doesn't matter, because it doesn't matter with deposit how much money you have in your bank account. The bank will always take more money, right? But withdraw is where we have the problem, because if we try to withdraw, but we don't have enough funds, then what we need to do is we need to tell the withdraw to wait until there are enough funds to perform the withdrawal. And so we open our lock, same as before, because we're potentially managing the balance. We then have a while loop, and this while loop will be stuck until the balance is enough to cover the amount. So if balance equals amount, this while loop will end. While the balance is less than the amount we're trying to withdraw, we don't perform a withdrawal. Further, we then say, we tell this condition, hey, if we enter this while loop, balance is less than amount. So we're going to say, hey, you know what? Stop here. Wait right here. Give up the resource you're holding. Give up the lock you're holding. And then proceed when you next get the resource. And what will happen is, because this is a while loop, eventually this thread will temporarily, it will pause, and it will pause right here, and it will actually give up the lock. At which point, Colby, stop meowing. Sorry, he's going ballistic. At this point, we return to this line of code when this thread is woken back up. It will then hit this statement, oh, that's the end of the while loop. Come back up here, check this condition again. If the condition is no longer true, then we will proceed with the rest of the code. But if this condition is still true, we give up the lock again and we wait again. After the condition is met, after balance is no longer less than amount, we will proceed and we will update, and then finally we release the lock. So this says, hey, temporarily give up the lock, and we'll try again later. And by the way, this code will be uploaded after class. Now let's go to deposit. What thread do I need to wait for? If I reach this statement, if balance is not less than amount, if balance is less than amount and I reach this statement, what this means is that we have given up the thread because we don't have enough money. When's the next time we can reasonably check that we're going to have enough money? What function needs to be called for us to have any chance of having enough money now? Deposit, right? If we're trying to withdraw and there's not enough money, then we need to wait for deposit to be called. So deposit has this function, and this function signal all. What happens is whenever a thread gets paused because of the sufficient funds condition, it will not attempt to restart until it's received a signal. Think of like a bat signal going up, like Batman's waiting for the signal. All the threads that are waiting for this signal. This line of code is the thing that raises that signal. It says, hey, all the threads that were waiting, you can try again now. These threads that are paused here will not try to proceed until they are signaled. And as a result of this, if I run this version of bank account thread runner, and the bank account thread runner hasn't changed, deposit runnable hasn't changed. If I run this, you'll see I end up with a balance of 0, which is good. But no matter how many times I run this, if I scroll up, I will never have a negative bank account. No matter how many times I run this, no matter how much bad luck I get, this will never allow me to have a negative bank account. Just to illustrate that. And again, that's because we have this condition check, and you pretty much always put the condition check as a while loop, and then inside of the loop you call await on the condition. And remember, this condition, sufficient funds condition, is tied to the lock in the constructor up here. This is where we tie the condition to the lock. So in this case, the condition actually is neatly tied to the lock, whereas in the case of the variable balance, it's only tied to the lock because we as programmers do it. In this point, Java actually ties the lock and this condition together. So again, the condition is used to say, hey, we can't proceed yet, let's wait, let's try again later. Signal all is used to tell all the waiting threads, hey, you can try again now. All right, so now I'll take questions at this point about any content or about what I just covered. I just wanted to make sure I got through the lecture in 50 minutes as much as possible, just because some students actually can't stay later, and they would want to ask questions about the later content, potentially. So, in-class activity. There is an in-class activity today. Does the condition require an import? Yes, it does, and it is up here, right there. It's the same library, so I'll go ahead and paste all the imports once again in here, but they're available. Is there a way to signal only a specific condition? Remember that there is only one condition, but there are multiple threads tied to that condition. There is no way to signal a specific thread. Remember, threads are chaos. There's no line. It's just a mad rush. They should be due at 6 a.m. tomorrow Eastern. That's not to encourage people to put it off that long. That's just to deal with time zones. If today's is due at midnight, I can correct that. Do we get unlimited submissions for homework 5? Correct. We were going to reduce the number of submissions per homework, but then COVID-19 happened. So we're not doing that anymore. There can be only one condition per lock. No, there can be multiple conditions per lock. I've never found a situation where I've used that. I've never found a situation where I've used that, but I'm sure someone could concoct one. You can have multiple conditions per lock, yes. I will check into that. Okay, I'll look at the deadlines there and I'll see what I can do. I need to, because there's 3 other professors in the course, I can't do anything unilaterally, but I will raise this to the other professors and see what we can do. Do we have to use condition for all locks? Yeah, I've already made a lock without conditions. So this bank account has 2 locks. This was example 5. It has 2 locks and it has no conditions. The problem is this bank account lets my balance go below $0. And if there's some condition where I can't allow a thread to proceed, if some Boolean statement is true, then the only solution, i.e. to make sure the balance never goes negative, is to use a condition like this. This is the only way to make sure the bounds never goes below 0. If I have no such condition that requires that, then certainly I don't need a condition. Is it ever beneficial to have a race condition? Not that I can think of. I mean, the race condition inherently means negative. That is to say, I mean, race conditions are faster, but your data will be useless. That's the problem. It's that you will have zero data integrity. So there's no way to know that your output is correct. Your output may be faster, but it's not at all correct. Does Homework 5 have automatic tests? There's two parts to it. There's a part on concurrency which has no automatic tests. It will be manually graded. There is a part on recursion, and it has automatic tests. So the recursion part is worth 50 points and is graded automatically. The concurrency part is worth 30. It is graded manually, and then there are 20 points for style. So WebCat for the recursion will give you feedback and a score out of 50. And it will give you feedback. But for the concurrency portion, it will not give you any feedback. So Homework 5, and there was an issue where apparently it was only giving 3 messages. I think I fixed that, but I will monitor this homework as submissions come in. And by the way, yes, we have not covered recursion yet. That's Friday. The recursion part of Homework 5 is not very sophisticated, and so you should be more than prepared to do the entire homework Friday, including the recursion part. Oh my god, there's a litter box in a closet down here, and a cat just really let one go. It is actually unpleasant. So I'm going to be doing this the rest of lecture. Sorry. Any other questions? Yeah, I need to get one down here, so I want to put a cat door in the door to that closet so the air can't escape, but I can't go to the store to buy a cat door or the tools to put one in. And therein lies the problem. Because we moved in right as the COVID-19 basically made landfall in the US and started going really big, so I'm trying not to burden Amazon with anything other than necessities, because Amazon's overloaded and the workers, they're not choosing to go to work because they're heroes. They're choosing to go to work because they don't want to starve, and so I'm not trying to make their lives harder right now. I can afford a cat door. I just can't get one in my house right now. That's the problem. And I also don't have a jigsaw, and I'm gonna need a jigsaw to put the cat door in. My stepdad has a jigsaw, but my stepdad is incredibly vulnerable because of respiratory issues to COVID-19, and so I can't visit him right now, which is sad because my stepdad's a very awesome person. All right. With that, then, I'm going to wrap this up, and I will see everyone Friday. Hang on. Are there any kitties down here? I didn't get to show off any cats today. Oh, I assume people want to see a cat. Unfortunately, Stuart's the most social with me, so he's the only one who's down here right now. Hi, everyone. This is Stuart. He is 10 years old now, so I've had this kitty for a long time. Take care.